We learned that the difference between steady state and transient heat transfer problem is the existence of the transient term in the governing equation. It's a term consisting of density, specific heat, and time derivative of temperature. Clearly, the time derivative of temperature indicates that we're now solving a problem with respect to time. For density and specific heat, these are two related material properties which will be discussed in this lesson. Let's start with density first. Considering holding the same volume of cotton and steel by hand, you will definitely notice that steel will be heavier. This is because cotton and steel have different weight, but weight depends on the gravity and hence changes with location. For example, your weight on the moon would be a sixth of your weight on the Earth. What does not change with the location is mass. Mass is a property that belongs to the material and is independent of gravity. And density is the mass per unit volume for the material. Now, let's move on to the specific heat. It's a term used to describe that for a unit mass of the material, how much energy is required to raise the temperature by 1 unit. For example, here is a 1 kilogram of water. To increase the temperature by 1 Kelvin, the needed heat energy is 4,180 joule. Accordingly, the SI unit of specific heat, as shown here, is joule per kilogram Kelvin. Since a unit increment of temperature in the Kelvin scale is equal to a unit increment in the Celsius scale, the unit of specific heat can also be written as joule per kilogram degree Celsius. Now, imagine you are going to a beach on a hot summer day. You will find that although the sand is quite hot, the water remains quite cool. Why is this? It's because water has a high specific heat. A material with high specific heat needs more heat energy for the same temperature increase. And this is why people say oceans are natural heat sinks for the Earth. On the other hand, since sand has low specific heat, it can get heated up very quickly. While specific heat is a useful quantity, by itself it might not give the complete picture. Often in design, engineers consider a certain volume for the thermal performance of the system. So the quantity we're interested in is the product of specific heat, density, and volume. This product is known as the thermal capacitance or thermal mass. Note that on the right-hand side of the transient heat equation, we have a term that is thermal capacitance for a unit volume. An interesting observation here, for many materials, if the density of a material is high, the specific heat of the material tends to be comparatively low. Therefore, in engineering applications, you might find that the product of the specific heat and density ρ times C does not differ drastically between different materials. Of course, this rule does not apply to all the material though. If you recall, in the previous section, we learned about steady-state analysis and the thermal conductivity of materials. And in this lesson, we're discussing about specific heat. So what exactly is the difference between thermal conductivity and specific heat? And is there any relationship between them? Thermal conductivity and specific heat each plays a unique role in the thermal behavior of a material. And in most cases, we need to consider them together for choosing an appropriate material for product design. Specific heat is the capability of a material to store heat energy in time. Note that in the transient term, the thermal capacitance term is multiplied with the variation of temperature with time. For thermal conductivity, on the other hand, it is the capability of a material to transfer heat in space. In Forest law, the thermal conductivity is multiplied with the variation of temperature with spatial coordinates. Both aspects should be considered by engineers in thermal design. For example, a material that neither conducts heat well nor changes temperature much with heat may act as a good heat insulator. On the other hand, we may have materials like metals that are good conductors of heat that also change temperature quickly, so that is ideal for cookware. We can see the usefulness of these three properties, conductivity, density, and specific heat, in describing the thermal performance of a material. It is worth noting that there is another property called thermal diffusivity that attempts to characterize the thermal behavior with a single parameter. It is the ratio between the thermal conductivity and the thermal capacitance for a unit volume. So for a unit volume, a material with high diffusivity generally has a high thermal conductivity and low thermal capacitance, as seen in case of metals. Such materials get heated up quickly and also conduct heat from one part to another part rapidly. Materials such as air and styrofoam have low thermal conductivity and high thermal capacitance for unit volume, so they have low thermal diffusivity, and thus heat doesn't spread through materials very quickly. The unit of thermal diffusivity is meters squared per second. The heat energy unit joule and temperature unit get cancelled out from the numerator and the denominator based on the definition. After the introduction of different thermal properties, let's see if we can evaluate these terms for a simple case in real life. Say you're in a park on a hot summer morning. There's a wood bench and a steel bench. Which one will you choose to sit on? Based on our life experience, we might prefer the wood bench because it is expected to be less hot compared to the steel one. But why is this? Let's have a look at the thermal properties of the two benches. Here we assume that the wood bench and steel bench are designed to be the same, that is, the volumes are the same. The specific heat of wood is larger than steel material, meaning that for same mass, wood needs more energy to raise the temperature. However, the density of steel is much larger than wood, making the thermal capacitance of steel much higher. This seems to indicate that the steel bench is slower than the wooden bench in heating up. Does this mean our choice of sitting on the wood bench a bad idea? In fact, thermal conductivity plays a key role here. Steel can conduct heat much faster than wood. If we calculate the thermal diffusivity, we'll find that the value of steel is larger than the wood. So our choice of sitting on the wood bench indeed is wise. In this lesson, we learned what the specific heat of a material means and how it affects the transient behavior of a material in a thermal analysis. In next lesson, we will learn about applying these concepts to a couple of practical engineering applications.